I haven't updated the LO2 makeups yet, Mango Mutiny. It's on my list. It's one of the next things. I had a few other things I had to take care of. LO3 had to get out, so people know whether they have to do the lab tomorrow or not. Those are out, by the way, if you did miss the Piazza post. Check out your LO3, especially the reading, to make sure you know whether or not you need the makeup opportunity tomorrow or not. And I had to get the homework 3 deadline extensions out so students know whether they need to keep working or not. Those are always a priority. Whenever a student needs my decision to make their own decision, those are going to take priority. For the LO2 makeup, the next LO2 makeup opportunity, I believe, is the last week of class. I don't think there's another built-in one in LO4 or 5. So that's just a little less priority, just because I know you want to know, but you don't need to know to make your decisions, if that makes sense. But that all the crucial ones are out there, so that's the next thing on my list. I got an email for LO2 makeup today. I'll have to straighten that stuff out and process everything, make sure everything's up to date. LO2 makeup interview. I thought the head TAs already did those. Yeah, interview for homework 3 this week. And that's another reason I needed your homework 3 code and extension results out early, as soon as possible. Because that means if you didn't get the extension, you don't have to do the interview. There's no point in doing the interview. So I can save you a little time in that sense. I mean, I'm sure that's not what you want. You'd rather just get the extension. But you don't want to do the interview and then find out you didn't get the extension and the interview didn't count anyway, and you could have been spending that time doing something else. Do I get another? I missed the LO3 interview last week. Yeah, you'll get more. For learning objectives, as long as you're showing me that you're trying, I'm going to give you opportunities, because I'm not going to let you fail on a technicality. Even if it is, you missed an interview, you should just be showing up to your dang interviews, scheduling your interviews. But I'm not going to fail you for that if that's the only thing you're missing. So for learning objectives, I'll give you opportunities. You'll have more opportunities. For application objectives, you might not get very many opportunities, since that's where you're working towards your A. If you get an extension, still need the interview. We will do homework makeup interviews in certain cases. But those will be, we'll reach out to you in those cases. Are we supposed to be interviewing if we got the extension? If you intend to complete the assignment, yeah. Did you upvote your own post, Slug Lovers? Come on. So if you intend to finish it, so ideally what you can do is schedule your interview, finish the code before your interview, and just be done with the whole assignment at that interview. Just show a full working demo and you're done. If you don't have things working, you can still interview, and sometimes I'll give you credit for the interview and say, finish your code in Autolab and you'll get credit for this, and you won't have to re-interview after you finish the code. Yeah, if you're having family issues and you missed an interview because of that, yeah. You missed an interview for family issues, I'm not going to fail you in the course because of that. You can relax. I'm not that cruel. I'm very generous with the learning objectives, as long as you have completed the 3 bullet points for that learning objective and the 15 bullet points for the whole course. If you actually can do all those things, I'm going to work with you, make sure you get past the course. I'm not going to fail you on some technicality like that, especially with legitimate issues. Don't worry about that. I know that's one of the side effects of this grading structure, that you can get scared that you're going to fail the class when something like that happens. I'm not that cruel. I'm not going to let that happen. For application objectives, you might miss an application objective if you miss a homework deadline. Maybe you had something go on there. That you might miss and get knocked down to an A- or B+. But I'm not going to just fail you because you missed something. I'm not doing that. I don't play that game. It was literally 2 hours ago. This is going to be an easy class then, for those of you in 191. All right, so with that, let's get started with some graphs. Where LO2 makeup's grades updated? Not yet. I feel like I just talked about that. Yeah, Hamza. The opportunities for learning objectives, that's to counteract the 5 or fail nature of it. That you have to complete all 5 learning objectives to pass the class. The makeup opportunities are to counteract that, so that's less harsh. The whole point is that those 15 bullet points and those 5 lecture objectives, Like, I need you to know, like, that's what you need to get out of this course. You need to be able to do those things. And the grading structure is just enforcing that. I don't care if you don't know learning objective 1 like right after you see it in lecture. Maybe it takes you some time to understand learning objective 1. So I'm going to give you the makeup opportunities towards the end of the semester and all throughout the semester. As long as you can get them by the end of the semester, I'm going to pass you in the course. But you can't just not understand stack and heap memory and then move into 220, because 220, Dr. Blanton's going to expect you to understand stack and heap memory, and he's going to build on that understanding. And he's going to talk about not just references, but also pointers. And you really, in memory management, there's no garbage collection. If you don't even understand at a basic level how that works, you're going to fail 220 if you don't work really hard to catch up and study over the break, granted. So I need you to know those things. And the grading structure is just there to reinforce that. Like, here's the stuff you need to know before you move on from 116. And then everything else, the structure just kind of evolves out of that. If you got an extension, just go to the interview and interview with whatever you got. You know, having something on record. If I see that you skipped the interview, that's going to look way worse for you than if you went to it and did poorly. May solvers due November. Hold on, let me, before we get into this content, I got to make sure it messes up the deadline. November, so homework's out. It should be due right here. Yeah, November. That's how it always was, right? Or are you just giving everybody a heads up that the deadline's coming up? So May Solver, I just released this morning, by the way. The doc's up. The pre-lab is baked into the assignment description again. And the grader's up. The auto grader's up. I meant to mention that earlier, so thanks, P. Good thing I was still reading chat 8 minutes in here, because that was a one I didn't want to miss. That is up. It is due in a week and a half for the first deadline. So make sure you're showing me good effort. And for the homework extensions, one of the big things that I look at for homework extensions is your first submission time. Those of you who've made your first submission right before the deadline, like I'm much less likely to give you a deadline extension, because it just looks like you slapped something together at the last minute, tried to submit, just hoping to get the extension. Like, that's not an honest effort. So even if your code isn't working, when you first start working on your code, submit regularly. Don't, because I suspect some of those students were working on it earlier and worked on it for a few days at least, but didn't have anything that they thought was worth submitting, and then waited to the deadline and said, the deadline's here, I'm just going to submit what I have. Make sure you're submitting at least something before you end for the day, before you end the work for the day. Just submit whatever you have, just so I have a record to know that you have been working on it. It's going to definitely help out on those deadline extensions. It's going to help you out on those deadline extension decisions. Because, I mean, some students, you know, we just did functional programming, and I would see first submission submitted November 1st at 11:57 p.m. And then I'll look at their code. I won't rely solely on that. There are some students who submitted at the last second, and I gave them the extension after I looked at their code and saw a lot of effort. But if you submitted it there and then your code is just a pile of something, mostly one of the other big factors was if they submitted at the right next to the deadline and didn't have any of the testing. I give you testing in the homework description for homework 3 and homework 4, and I will again for homework 5. I give you the tests right in the description. If you didn't even code up those tests, like, come on, man. That's like skipping the pre-lab. And as we all know, skipping the pre-lab factors into your deadline decisions. Yeah, and I do think this one is, you know, as you're saying, 5 hours easier than the previous 2 assignments. So you can hold me to that. If you disagree, you can let me know. But I think this one's easier, especially if you do the today's and Friday's lecture questions. It's not too much more than the lecture questions. I think this homework is a much softer blow than especially the previous 2 assignments. Anyway, we need to get into some lecture content. Today's lecture content isn't too... Like, I don't have to rip through this too fast, so we did have time for that 10-minute intro. Yeah, exactly. So these last two graders haven't checked your tests, so I guess there's less incentive to submit earlier to get that incremental testing when it just says whether your primary passed or not. But if you haven't made your first submission yet, you don't even know that that's the case. So these students weren't even submitting just to see what the feedback said. But yeah, I if I had testing, then it would make sense to submit the pre-labs. Like back in the pre-lab, it made more sense to submit once you wrote the test to make sure your tests are right and then write the code. But since you're expected to be more mature in your own testing for these later assignments, which is why I don't give that feedback now, is less incentive to test, but still, or less incentive to submit. But still submit. I'd say before you're done each day, you have a session where you're gonna sit down for a few hours working on the assignment. Whatever you have at the end of that, submit it, just so I can see that you're working. Show me that you care, and I'll help you out. I'll work a lot more with you. So the lecture question today is very similar to a lot of the lecture questions in this learning objective. There's a graph class in the examples repo. Grab that class. It has two stubbed out methods. One is are_connected, and the other is distance, which distance is going to be Friday's lecture question. It's already up on AutoLab if you want to get both of these done and look ahead a little bit. These methods are stubbed out. It just says to do, finish this. It's going to be a lecture. I don't think I say lecture question in the repo, but it says to do. That's where you work on it. And this is going to take two ints, which denote nodes in the graph, and determines whether those nodes are connected or not, and returns true or false. True if they're connected, false otherwise. And then a test suite, test connected, to test this functionality. And there is an example graph in the repo as well. There's a sample main method where I show you how to create a graph and everything. If you want to just cut and paste that right into your tests, I won't be mad at you. Just grab that graph instead of building the structure for a whole new graph. And that example is the one we're going over in lecture as well. So hopefully that all that overlap helps you write that test. The only easy thing in 191 is graphs. Well, this lecture might be super easy for y'all then. All right, so a little bit of review. These data structures are so crucial to a well-rounded computer science education. So I want to do a little bit of recap. Obviously in 250, you're going to dive deep into the structure and proofs and runtime of all these data structures and different operations. In 191, you're seeing some of these data structures as well. Excuse me. And in 115, 116, you've seen these data structures, a couple of them as well. Oh yeah, I don't have JSON on here. I guess you could consider that another data structure. But that's kind of just a combination of the first two, I would say, if I think about it. So we saw sequential data structures. These are our arrays and linked lists. We have elements that are stored in a specific order, and the order matters for these. If you could go back to 115, no dice. You can, but you don't want to. You don't want to waste your time. So we have data stored in a specific order, whether that's their one continuous block of memory indexed based on their memory addresses, or separate nodes in the heap, separate nodes in different memory addresses that have references to the next node in a linked list. Either way, this is just storing a sequence of values in two different ways of representing that. We also have key value stores. These were our dictionaries in Python, our objects in JavaScript, our maps in Scala. We have some key that maps to a value. The order for these does not matter. All we know is that at some key, there's a value at that associated with that key. So the key CSE maps to the value 20. The key MGA maps to the value 3. The key Geo maps to the value 5. There is a method that does that for a list, where we have the apply method, and you can use the parenthesis notation, the same as arrays. But what that does, if you say .apply of 2, what that does is follows two references. So it'll start at the first node, and it'll jump. It'll follow one reference, two references, and find this value. So we pretend that that's an index, but it's a linear runtime lookup, whereas with an array, it's an O of 1 runtime lookup. So there's a difference. It behaves the same way, but it's very different in efficiency because you have to follow all those nodes. There's no way to go from this node to this node. There's nothing you can do to compute how to get there from here without going through this node. With an array, that's not the case. You can start at this and just do some math and say, okay, I'm at this memory address. I'm just going to jump up 2 memory addresses and find the next value. So if I have, say, 32-bit ints in this array, I'm going to jump up 64 bits, and I'm going to find the third value in this array. I can get there directly without ever considering or looking at this value. So that's the difference in that. The syntax in reaching those elements in our code is similar, but what they actually do, very different. And finally, we saw a tree. This is our first, I don't know if I want to say it like that, but kind of looser structure, or more complex structure, I suppose, where we have a root node, which can map to 2 different values instead of just 1 different value, like a linked list. And then we could have this branching structure to be able to have a lot of values. And we can actually have, I didn't show it in this class, but we can actually have key value pairs inside our map, inside our trees. So our tree can have, instead of just a value, can have a key and a value. We can do the same thing with a linked list, though that's less beneficial. If we have a key and a value, and then have the tree organize itself based on the keys, and then look up the values, to a way that we can have a kind of a sorted map where we're sorting based on the keys, and then have each of those keys still mapped to a value. So there's different things we can do with that. We just did it with values in this course because we didn't need to add more complexity to it. All right, so that's kind of a review of the different types of structures. Obviously, there are different ways that we could build this. I just mentioned a way you could build a key value store out of a tree. There are different things that we can do with all these, but these are like the 3 general, like high level, what we call abstract data types, abstract data structures that you know about so far. And then in 191, you also know about sets, which is an unordered, kind of like a key value store, unordered values, but without keys and values, just the values and no duplicates. So kind of like a key value store where the key maps to itself in a way. I guess you could think of it like that. But anyway, the key point of there is you don't allow duplicates, which you're well aware of from 191. And actually use a set in today's lecture. Or maybe Fridays. I think it's today's, though. So my question for you, knowing those 3 types of data structures, what if we had data like this? What if we had data representing intersections and roads connecting those intersections? What if we had subway stops with connections between those stops? What if we had servers on the internet that are connected to each other? This map from the very early days of the internet, which is actually the one I'll use for the examples throughout this lecture, where we have all these locations with servers and then connections between other places. How do we represent this using the data structures that we have? And of course, spoilers, we're going to use a graph for this. So we can't really represent this data in the structure, any of the structures that we have so far. We're actually going to use a combination of a few of them to represent this information. But let's just try to use one of the structures. It feels like this should be a tree. If we look at it, if we're seeing nodes and then connections between the nodes, really starts to feel like a tree structure. So let's try that. And let's build out our tree. We're going to start at one of these nodes. We're going to start at UCLA. And then we're going to use that as our root of our tree. And then have references to all of the children, which are going to be the connections, the servers that UCLA is connected to. So Stanford, SRI, UCSB, and RAND. We're going to have connections to all those. So those are going to be the children of UCLA. Then we're going to go to each one of those and and store a reference to each one of its children. So I won't build out the whole thing, but we can see the problem right away. When we're at Stanford, we're going to build the children based on the connections. We have SRI and UCLA. And right away, we already see that we have duplicate nodes in this tree. We're going to have SRI represented twice, UCLA represented twice, and maybe we could add some extra logic and say, well, Stanford is already referred to by UCLA, so let's not add that connection right back. We could eliminate that with a little extra logic. But SRI is going to be trickier. So UCLA refers to SRI. We would have to go back through the tree, find that, and notice that we shouldn't have that duplicate. And we're going to end up, if we don't do something to prevent that, we're going to end up running in cycles. So SRI is going to have UCLA as a child, which is going to have Stanford as a child, which is going to have SRI as a child. And this tree, if we're not careful about what we do, is going to go infinite. We're going to just start running around in what we call cycles. And we're going to keep moving around in these cycles if we don't add some extra logic to be able to prevent that. So a few reasons why we don't want to represent this with a tree. But let's try one quick modification to a tree. And instead of adding the duplicate elements, we're going to do kind of what I said earlier. We're going to look in the tree, or the graph is what this is going to be. And if that node is already in the graph, we're not going to create a new node. We're not going to omit that connection completely, that reference. What we're going to do is find that node already in the graph and create a reference to that node. Or more accurately, as we'll see with graphs, we're going to add that connection in the graph data structure. So these are no longer unidirectional connections. These are saying Stanford and UCLA are connected. MIT and BBN are connected. It's not a one-way reference. They don't store references to each other. They're going to be connected in this graph. So now we solved our issue. We just said, let's have one node for each value that we need to represent from our data, and then add in the connections between any pair of nodes in this structure, in this data. It does look like a neural network web, or an RDBMS. I haven't seen that one in a while. Relational Database Management System. I haven't seen that in a while. So we have the nodes that all have these connections to each other. So there's one big problem with this. Based on what we know so far, what if we want to do something simple like traveling to each node? We just want to visit each node. In trees, we used our tree traversals. So we had a node. We would visit that node at some point, either before or after, during the recursive calls, and we would recursively call the traversal on each of its children. So with UCLA, let's recursively call on one of its children, recursively call on one of its children, recursively call on one of its children, and oops, we got stuck in a cycle. We're going to be spinning around this forever. We're going to get a Stack Overflow. We're going to get our infinite recursion. Bad news. Our traversal algorithms, we have to throw them away because we have what we call cycles. Once we have a loop that we can move around and reach where we started before, and it doesn't have to be this small loop. It could be this loop right here. Could be this one right here. Let's zigzag around a bit. Oh, I doubled SRI. But you get the idea. I can travel around in circles. And same with like if we want to represent intersections and the roads connecting them, we have the same problem. Which in the real world, this isn't a problem because we don't always want to travel back to the root intersection if we want to go somewhere else. We want to be able to take the shortest path between intersections to be able to get to our destination. It's a good thing in the real world. It's a good thing in the internet. We don't have just one connection that can be severed and disconnect the entire internet. But we have to generate new algorithms to work with data with this type of structure. Exactly. And that's where we're headed, like a Google Maps type algorithm. So if I want to find the shortest path, which is your maze solver homework. You don't have to just solve. It's not enough to just solve the mazes in the homework. You have to solve them optimally. So you have to find the shortest path from the start to the end, algorithmically, with your code and everything. So that's what we're going to end up doing, which is the similar at least, logic as Google Maps. Of course, Google Maps is more sophisticated and everything, and takes speed limits into account and everything else, traffic patterns and stuff. But it's the same idea that we're doing there, just a bit simplified because this is your first taste of it. Is there an interface for the maze homework? Yeah, there's two methods that you have to write. There's a lot of code that's given to you when you clone the repo, and then there's two methods that you have to write. It works on a grid system, and one of the methods is given the starting and ending grid location on an XY grid. Give me the path between the two, and you're given the entire grid, and certain tiles are marked as impassable, meaning they cannot appear in your path. So you have to navigate that. The impassable ones are the walls of the maze, and you have to be able to navigate through that. So that's already there. There's a to-do in the code that says do this one. Then the other method you have to write is given a path in your current location, determine the velocity that you need to move in to be able to travel along this path. So given a path in your current location presumably on that path, do the math to figure out which direction you need to go to keep moving down the path. Once you have those two, that's your interface that you're developing. That's the interface that interacts with my map. And then the handout code also comes with a server and a web front end. So you run your server, you implement your two methods, you run your server, you open up the HTML, and you'll have a maze and with a character, and then wherever you click, your character is supposed to move to that click using the optimal path. If you implement your two methods correctly, the GUI will all work. Red Jacket fire alarm. Oh no, we're sorry, but we're not going to wait for you. Traveling salesman with genetic algorithm and a twist. I mean, it's a lot simpler than that, though. You're overthinking it for sure if you try to take that approach. Yeah, take 312, web apps. All right, so how are we going to work with this? All of our known algorithms that we've seen already in 115, 116, not going to work. We got to think of something new. We got to at least make a modification. And just to foreshadow a bit, the modification we're going to make is when we're traversing the graph, we're going to check each time we try to go to a node. So we go UCLA, Stanford, SRI. Maybe that's not what we'll end up doing in the algorithm, actually, but it's a bad example. But once we have a case where we're at some node and we're about to travel to a node that we've already explored, we're just not going to do that. And that's going to be how we're going to get rid of this problem. So it's a modification we have to make to our traversal algorithms. Pretty simple one, but it makes the code a little more complex, and we have to explore the implications of it. So we also have to change the way we're representing these. We could try to represent these as nodes. I shouldn't say try. We could represent these as nodes just like we did with linked lists and tree, where each node has a list of references to the other nodes. We can certainly do that. We would get away with that. It'd be fine. But it's just not the way that we usually represent graphs. And it's not the way, more specifically, more to the point, it's not the way you're going to see graphs represented in 250 and 331 and 191. Actually, did you see adjacency lists in 191 today when you covered it? Did you talk about adjacency lists? Because that's what I'm going to show you. Or did you see adjacency matrices? Either one of those two? Maybe that'll be Friday's 191 lecture. Don't think so. All right. Maybe you'll talk about that on Friday. But graph representations is the... Oh, you did see the matrix. Okay. So the two big ways of representing a graph are adjacency matrices and adjacency lists. I'm going to show you adjacency lists. So it's cool you get both of them. And then you'll know both of them going into 250 and going into 331. It's going to be perfect. So we're going to represent these as nodes and edges. So each value here, each green box here is going to be a node, and each connection between them is going to be an edge. In 191, if you saw the adjacency matrix, you would have each one of these nodes as the rows of the matrix, and each one of those nodes as the columns of the matrix. Then you have a 0 in the cell if there's no connection between those two nodes, and a 1 in that cell if there is a connection or an edge between those two nodes. We're going to see this a little bit different. We're going to see an adjacency list, which is right here in all its glory. So we're going to store an adjacency list, which is a map of ints, in our case, when we get to the code, to lists of ints, or rather a map of nodes to lists of nodes, where for each node in the graph, we're going to store a list of all of the nodes to which it's connected by an edge. Yeah, taste of adjacency lists and matrices. Good. And either one, I mean, there are advantages and disadvantages of each, mostly in terms of big O, time complexity of your algorithms. But they represent the same information. So they just really change how you're going to code your algorithms in the time complexity between them. With adjacency lists, I usually lean towards adjacency lists because it's usually the more time efficient. Usually has more time efficient algorithms, especially if you, well, I guess depending on how you represent these, if you use, we don't need to talk about all this, but if we use hash maps, if we have a map of nodes to a hash map of nodes, it's really efficient. That's not true, is it? We'd have to represent this a few ways. Because if they're linked lists, it depends on the algorithm. We don't have to talk about that. I don't know why I went down that road. It depends on what you specifically need, which one's more efficient. So, in the code, we're going to create this graph where I have this little bit of bookkeeping. I don't want you to panic about it, though it has confused some students in the past, where each node is going to be represented by a unique ID, which is going to be an int, and then all our algorithms are going to work off of these ints. So the graph is going to store values of some type A, and for each node, we're going to have a map that maps its index to a value of type A. So given the index for a node, I can always look up its actual value. So I can ask this node's map, hey, node, what's the value for the node with index 2? And it's going to map to the value that's stored at index 2. And then my adjacency list is going to be a map of ints, which are the nodes, the IDs for the nodes, to a list of ints, which are all the indices, the IDs for all the nodes for which there is an edge from the one node to the other. There's an edge between UCLA and Stanford and SRI and Stanford. That's what this is saying. So UCSB, there's an edge between UCSB and UCLA. There's an edge between UCSB, I should have picked one with just one syllable, UCSB and SRI, and there's an edge between UCSB and RAND. And since our edges are non-directional, I forget the word for it. But anyway, since we don't have directional edges, which is something we're not going to see for graphs, kind of like we did with linked lists and trees, there was a clear direction for each reference. Since we don't have that, if we go to UCLA, we better see UCSB in that list. So UCLA, UCSB is in that list. SRI, UCSB is in that list. And RAND we're going to see UCSB in that list. So each edge appears in this adjacency list twice to denote that you can go both directions down that edge. So when we add a new edge to our list, first when we add a new node with some index and some value, we're going to add that to our nodes and add an empty edge list to our adjacency list. Then when we want to add an edge between two nodes by index, we're going to add that twice into our adjacency list. Once to say that index 1, there's a connection from index 1 to index 2, and once to say there's a connection from index 2 to index 1. So we're going to add that in both places. If I want to add a connection between Stanford and SRI, I'm going to say adjacency list of Stanford, prepend SRI to that list, and the adjacency list, I'm going to replace that with a new adjacency list with the mapping of Stanford to this new list that I created, which it includes whatever Stanford had an edge to and also SRI to it. So hopefully you can read this line. There's a decent amount going on, but if you're sharp with your maps, this is a key value pair, index 1 to this new list, which is created when I prepend index 2 to the adjacency list of index 1. And I'm going to reassign the map because this creates a brand new map, just like our linked list maps are immutable as well. This is going to create a brand new map with this new key value pair into this adjacency list. And since I'm reusing the key index 1 and we can't have duplicate keys in a key value store, this is actually going to replace the old adjacency list with this new one, which has index 2 prepended to it. And then same thing with the adjacency list for index 2. I'm going to grab that adjacency list, prepend index 1 to it, create a new key value pair, which maps index 2 to the new adjacency list with the index 1 prepended, and then update the adjacency list with that new key value pair, which replaces the key value pair, the value that index 2 was mapped to. So I guess there's a lot going on there. I didn't really think that there's so much going on because I just expect you all to be really sharp with maps at this point. But there is quite a bit going on here and a decent amount of syntax. So hopefully you're all able to follow that one. If you change int to string, still that method seems to work. So when you create your map of strings, well, we're just going to get to the example. When I create a graph of strings, A is going to be strings. This adjacency list is always going to be a map of ints to a list of ints. That's always going to be the same. But when I look up the value for each node, by its index, we're going to get that value, which in this case is going to be string. So if I create a graph of strings, first thing I'm going to do is add all my nodes, and I'm going to give each one of these nodes an arbitrary index. The only thing that's important here is that the IDs are unique. So I'm just going to generate a random number for each one of these nodes. Getting a headache, Kylins? Is there a specific question I can help you out with? I know it's a decent amount getting thrown at you, but I want to help you. And then when we add our edges, we're going to always add them by the IDs. So there's an edge between UCLA and Stanford. So I'm going to add that edge, 0 and 1. And that's going to add 1 to the adjacency list of 0 and 0 to the adjacency list of 1. So I can denote that connection between UCLA and Stanford. There's an edge between 0 and 2, 0, 3, 0 and 4, and so on. All the way to like 12 and 10. I'm adding that edge to say there is an edge between Carnegie and Case. And that's going to store all the values, that whole adjacency list. This whole adjacency list is going to end up in this list, but with the ints for the IDs that I assign to these nodes. And then this map is going to map each ID to its corresponding string, which represents the server that it's mapping to and that it's representing. Yeah, I guess this is where rhyming dictionary comes in handy. And copy and paste about to come in. Yeah, this is what I mean. This is what I was saying earlier. This example from the repo, if you cut and paste this for your testing for today and Friday's lecture questions, I ain't going to be mad at that. Use this as a starting point. And I would recommend modifying this at least at some point, even if you don't do it for your testing, just so you get a good feel of what this graph class is doing. Because you can guarantee on your learning objective quiz next Thursday, I'm going to give you code that looks like this, and I'm going to say, oh, it's tough in Google Forms, isn't it? How do I? Oh, I think I know how I do that. But I'm going to give you code like this, and I'm going to expect you to know what that graph looks like. So I'll give you code like this, and I'll ask you, what's the distance? We haven't defined distance yet, but what's the distance between rand and BBN? For example, that'll be a good quiz question. So you need to be able to read this kind of code. I would change this to like doubles or something, and make sure that you can rebuild a graph using this code. Submit an MS Paint document. You know, I could actually have you... Yeah, I could, but I just don't feel like dealing with the questions of I don't have Microsoft. What do I use for Paint? And there's got to be some web app for that, though. I don't know if we'll end up doing that, though. It's a lot easier when it's in... Yeah, Scribble.io looks like it'll be what I'm thinking of. I mean, yeah, I'm gonna take it seriously. It's a good question. I mean, it's a better quiz question if I say, here's some code, draw the graph, instead of asking you, okay, here's some code, here's some question about the graph, and just expecting you to draw the graph in between. Like the distance thing, if you're off by 1, maybe you know graphs and you actually drew out a beautiful graph with everything accurate, but then you just messed up your data, your distance calculation, and I gotta give you a 0 for that question. It's not the best. Google Docs has Google Docs does, but not Google Forms, because we use Forms for the thing. But Google Forms does let you upload files. So if I had you draw it and then download it as a file and then upload it to the form, is that just too much? That might just be getting too complicated, though. Or mail the graph. Yeah, me or the TAs don't want to go through all our email looking for graphs, though, is the thing. That just makes our logistics a lot tougher. But we might ask you, so Zoom does have a drawing thing. Maybe we'll just do that during the interviews. Or not at all. Probably not at all. It's just more logistics. So let's define paths. We ended in 6 minutes. Let's get through these. So a path through a graph is a sequence of nodes for which each two consecutive nodes are connected by an edge. Each two adjacent nodes are connected by an edge. So this is a path in this graph because I can go from UCLA. There's an edge to SRI. There's an edge to Utah. There's an edge to MIT. There's an edge to BBN. There's an edge to Rand. So this is a valid path in this graph. This is not a valid path because SRI to Utah to BBN, there's no edge between Utah and BBN. So this is not a path. That's all I have to say about paths. So I'm just going to pause for a second and just going to pause for a second and make sure that it sinks in. Gonna send a condolences card because that's what he'll see. What? Mail in answers. Breath first search in 5 minutes. Yeah, let's do it. So all of Friday's lecture is exploring BFS in more depth. Today is just introducing BFS. So yeah, BFS in 5 minutes actually isn't a big deal today because we're not getting into any detail. I'm just introducing what BFS is at a very high conceptual level. So yeah, 5 minutes. No big deal. Watch me. Breadth first search. So one question that we're going to have a lot in graphs that we do have is, are two nodes connected? And this is similar to our traversal questions as well. Doesn't a path also require that no two nodes are visited twice? No, we actually have another definition for that. We don't talk about in 116, but that's called a simple path if there's no cycles in the path. If no node is duplicated in the path, then there are no cycles, and it's a simple path. But a path can have a repeated node. A path that just runs around in circles 50 times, that's still a valid path by our definition. It's just not a simple path. For the Friday lecture, does the code you showed... you can ask... Oh, for Monday, you have to ask after the lecture content today. So the connected component, or just generally traversing a graph, just visiting every single node in a graph, is something we want to do fairly often. So let's talk about how to do that. And for two nodes to be connected, for today's lecture question, two nodes to be connected means there exists a path between those two nodes. So, anyway, so does there exist a path between these two nodes? For this graph, this is a connected graph because any two nodes, there is a path between them. You can get from any node to any other node just by following edges. If we remove a few edges, then this is no longer true. We can't get from SDC to MIT no matter what path we choose. We're stuck up in this connected component, or in these nodes are all connected to each other, but we're stuck in this connected component if we're over here. We can't jump over to the other one. So any node from here is not connected to any node up here. We just can't get there. So with a graph like this, we can just look with our eyeballs and figure out if two nodes are connected or not. And this was the early days of the internet when these were the only servers. But the internet's gotten just a little bit bigger since then. So what if we had to run this on the current internet? What if we wanted to know, does there exist a path of links that I can click to get from one site to another, for example? Would I be able to follow a path like that? And then what we'll talk about Friday, what's the shortest way, the least number of clicks to make to get there, which is actually one of my 250 assignments, was to actually use real data and figure that out. So to do that, we're going to do breadth first search. And for this, the algorithm, we start at some node, any starting node. For your homework assignment, just one of the two nodes that you get. Your assignment, your lecture question today says, are these two nodes connected? Just arbitrarily pick one of those two nodes as your starting point, and then we're going to explore all of its neighbors. So we're going to take each edge connected to that node and add them to a set of explored nodes. Then we're going to just keep doing that. We're going to do it again and again and again. We're going to visit every neighbor, which is what we call two nodes, nodes that are connected by an edge. We're going to traverse each edge from all the nodes that we just explored. And we're going to keep repeating until either we explored all the nodes in the graph, or we have a step where we explore all the nodes and there's just nothing left to explore. Or actually, more succinctly, it's just when there's nothing left to explore. If you traveled everywhere, if you visited every node, that would be the same thing. So we've explored all these nodes. There's nothing left to explore. So we're done. And these are connected nodes. And for the lecture question, you would say, okay, I started at index 1. Here are all the nodes that I explored, and there was nothing left to add in the last round. Did I explore index 2? True or false? That's what I return. And you have the code for BFS in the repo. So it's modifying that code to check if you ever visited the other node. And never visit a node twice, so you don't get in any infinite loops. So in the code, we're going to have a set, which we don't talk about the structure of a set in this class, but it's just like sets that you've seen in 191. It's a data structure that doesn't allow duplicates, and we can insert by adding, like a map, same syntax, and we can check if it contains certain values using this contains. Those are the two methods that we'll need here. So we're going to have a set of all the nodes we've explored. We're going to use a queue to determine which node we're going to explore next. We're going to enqueue the starting node. We're going to start at some node ID in this graph that we're given. And then we're going to start our loop. We're going to say, well, there's still something to explore. Explore it. So we're going to check the next node in this queue. We're going to dequeue it. And we're going to visit that node by exploring all of its neighbors, any node that's connected to it by an edge. So we're going to iterate over all of its neighbors. We're going to use the adjacency list of the graph for that. The node, whatever we're exploring, so say we're starting at UCLA, we're going to iterate in this loop. Node is going to be Stanford, SRI, UCSB, and RAND, one at a time. And for each of those nodes, we're going to check, have we explored this node yet? If we haven't, we're going to explore it, which is to say we're going to add it to the queue. So we're going to say this one, once everybody else in the queue is done, we're going to explore this node's neighbors next. And then we're also going to mark it as explored. So we make sure we never add a node into the queue more than once. So if the node is not in the queue, if the node has not been explored, mark it as explored and add it to the queue. So we're going to keep iterating over this. We're going to take the next node in the queue, explore all its neighbors. If it has not been explored, add it to the queue and explore it. And keep going until there's nothing left in the queue. Once the queue is empty, we're done. And then you can check, hey, I'm wondering if these two nodes were connected or not. I started at one node. Has the other node been explored? Today's lecture question is not difficult. It's probably one of the tougher ones to wrap your head around. But once you understand what to do in terms of writing code, it's almost nothing. Since I give you BFS, you can take my BFS algorithm and modify it. And there's not much modification you need to do. You just need to check, is the other node in the explored set, which you have a contains method for. So the code for it. But thinking about how BFS and graphs work is going to take you some idea. So start at node A. To check if two nodes are connected, start at node A. If you explore node B during the algorithm, they're connected. If you get to the end of the algorithm and node B was never explored, not connected. Do we have recursion example? No. So there's breadth first search, which we're talking about here, which works well with iteration. Doesn't really call for recursion. And then there's depth first search, which explores the nodes in a different order. So breadth first search does it in this order. We start at a node and then explore all of its neighbors and then explore all of their neighbors. And we're growing out, in a very particular way. In depth first search, we would explore just one of the neighbors and then move to this node, explore one of its neighbors, 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 explore one of its neighbors. By the time we get here, there's nowhere else to go because all of its neighbors have been explored. And then we would start returning and moving back up. That lends itself very well to recursion. So if we were doing depth first search, which I wanted to add to this class, but it's just a little too stuffed. It's one of the things I would like to add. If we did depth first search, then we would use recursion for that because it makes writing that code so much simpler when you're doing it like that. But breadth first search just lends itself well to a loop instead of recursion. There's really no need for recursion. It might even be, I don't know, I haven't tried it, but it might actually be a little tougher with recursion. We'd have to pass the explored set to all the recursive calls and across the stack frames. It would be a little bit trickier. For explored, could you write plus equals instead of calling itself? Yeah, this could be plus equals. I don't know why I kind of, sometimes I use plus equals, sometimes I don't. I should be consistent with that, either always use it or never use it. But yeah, I could do explored plus equals node right here. We're making explored a list and called distinct. Yeah, I mean, we could do that. That's just one extra step. And actually, I don't. Actually, why do I do a set? Why do I even use a set here? Maybe just for efficiency. I think I used to need a set, but I changed my implementation a bit that I just don't need a set anymore. Because I always check if the node is in the set or not. If the node's in the set already, I'm not adding it. So I'm not taking advantage of the duplicate, not allowing duplicates anyway. But I think I used to have, the way I had my breadth first search written at some point, I would just add all of the neighbors to the explored set and let the set remove the duplicates for me. But I'm not doing that anymore, so I guess I don't really need a set here. Yeah, for efficiency, a set is more efficient for this. Maybe that is. Maybe I was worried about efficiency when I wrote this. You know what? I think I wrote this code when I taught 331, to be honest, and where I was worried about efficiency, because if I'm not worried about efficiency in 331, I'm not doing my job. So I think that's why I use a set here. Because of the set, a proper implementation of I shouldn't say proper, but with a certain implementation of a set, contains and adding to a set should be O of 1 operations if the set's built on a hash table. Let's check. I won't belabor this. I won't go too far into this because I might go down a bad path here, but let's try quickly. To try to check if this is built on a hash table or not. Not seeing any clues. This is just the trait. So what's the default set? That's what I need to know. I would need the set object, right? I want to go here. No, I want to go here. I'm curious now. I'm going to take one more shot. Where's that? Not what I want. Not what I want. Not what I want. Now it's bugging me. Thank you. It took forever. So a list set. I don't know if this is worth it after spending this much time. So if I did a list set, and it's not built on a hash table. Oh boy. Pretty clearly built on a list, given the name. Alright, well, it was too much of a rabbit hole. Per the doc, it says beyond that. So it's hash tries. I went to so many docs, I don't know which one you're talking about, though. Wi-Fi. So beyond a certain size, they're built on hash tries. Like tries, not. Oh, because I'm using immutable instead of mutable. Okay. Wait, so what I was supposed to look at is right here for the mutable type hierarchy. In set is a hash set. Oh, that's what. I guess that makes sense, because why would you build a hash table and make it immutable? You wouldn't get any of the performance out of it. So if I use a mutable set, that's what I should be using for optimal efficiency, for peak efficiency. All right, well, I missed the target on that a little bit. But at least when I did it in 331, I could say, like, we're going to use a set here because it's built on hash table, even though it technically wasn't in my example. The point remained, but the efficiency was not there. Is it 116 material? The depth, so it's DFS and BFS for depth first search and breadth first search. We only do breadth first search in 116. I'd like to do depth first search, just so I can get another example of recursion in the course. But I don't have any application for it. As we'll see with breadth first search, that's actually what's going to allow us to find shortest paths in that for the maze solver homework. We'll be able to do that with breadth first search, but we don't get the same property with depth first search. We're not going to be able to find the shortest path or anything useful, in my opinion, with depth first search. So I'd be throwing it in there just for an example of recursion, and I wouldn't get any extra value out of it. I wouldn't be able to say, here's depth first search, here's how we do it, we use recursion, all this mind-bending stuff, and I'll show you the stack again and how things are working. And then I'll be like, wasn't that neat? Okay, cool, we're moving on. Kinda, to be honest, kinda like what we do with trees, but I can't cut trees out of the course. Where I don't have a good application for them. With trees, I tried to get a good one last semester with, I had homework for decision trees. You would build out a decision tree where each node asks a question, and then you traverse the tree, and then make a decision. Kind of like a 20 questions game. If you play 20 questions, you ask a series of yes or no questions, and then you can traverse a decision tree. That's how if you get like the toy that does 20 questions, and it asks you a question, you click yes or no, and it guesses whatever you were thinking of really phenomenally. That's because it uses a depth 20 decision tree to make that. So then the homework was, given a bunch of data, build an optimal decision tree, which made it a bit tougher, but then students found out how to cheese the assignment. They just manually built their decision trees instead of writing code to build it. And I don't know, it had problems. But I don't really have applications for trees either. I'll have to get a better one at some point. Can I explain the set syntax for BFS? So a set is a data structure that it's unordered and it doesn't allow duplicates in the list. And it has efficient lookup. You can ask if a value is in a set efficiently, and efficient inserts. Though as the rabbit hole we just went down, apparently we don't get that with the immutable set, which is the default in Scala. But with a mutable set, you do get those properties. So if you want to swap that out for a list, be my guest, since we're not worried about efficiency in 116. And the code already controls the duplicates. If you had duplicates, it just muddies up the data structures. So like if I had it depends how we mess it up, but it can, like if we get the same value in the queue multiple times, we're gonna waste some time spinning our tires and potentially open us up for an infinite loop in the worst case if we mess it up horribly. Yeah, mundane man band. I got to answer this, and then 442. The activity is posted, and the auto lab is set up. So you feel free to take a look and get started. I'll formally introduce it, but I got to at least answer this question because he asked during lecture, and I said ask again after lecture, and then I just didn't get to it till now. For the Monday lecture, does the code you showed account for find not actually having the value? Didn't hear it explicitly. Oh, I know what you're talking about now, because we did trees, we did BSTs. Find is going to return null if it doesn't actually find the value that we're looking for. So yes, it does account for that. See if I can pull it up real quick. So find, if we get to the base case and the node is null. So we compared, we moved either left or right with a recursive call, and we called this on find helper of A and null. That's going to be handled by the base case. Node is null, so return null. So if this method returns null, that means the value is not found. Otherwise, our base case is actually finding the value and then returning that node. Depth first search is not 116. It could be. I mean, it's within reach of 116. It wouldn't be inappropriate to add to the course. I just don't have room in the schedule for it. And since there's not enough excitement, there's nothing exciting I can do with it that I've thought of yet anyway. There's no, there are other things I'll add before I add that are more exciting. Oh, cool, you got it, P. Good. The one that tree that I just took forever to find. That's the one I was looking for. I wanted to find that map because it shows the default implementations. These bold lines are the default implementations of things.